All right, so welcome to DataLab3. Today we are going to look at indices of intra-individual variability. So when you have a time series of how something is fluctuating, in my case, I'm going to be looking at happiness across time. How can you kind of quantify interesting dynamics in the time series for each individual so that then you can start making between-person comparisons between people in terms of the dynamics that they are displaying in their constructs of interest to you. So that's kind of the big picture. So again, we're looking at the same daily diary data. You want to start off by letting Aura know where your data are. And then we're loading two packages that might be useful. And we're importing our daily diary data. This is a really nice resource. It's a great paper that came out in the past year or so. And it goes into a lot of detail on complex affect dynamics and suggests that they add limited information to the prediction of psychological well-being. It's a really important paper. We're not concerned about this particular part or even the fact that it's affect dynamics. What you will find most interesting with this paper for the purposes of the current course is table 1, which has a really nice overview of commonly studied indices of intra-individual variability, a few of which we're going to go through, actually almost all of which we're going to go through. Not all of them today, but some of them today. So that's there if you need to find it. And I highly encourage that you read it if this is stuff that is really interesting to you. Okay, so the first thing we're going to do is we're going to just take the average of a person's time series. So the intra-individual mean, we're going to take the sum of all ratings divided by the total number of completed measurement occasions. And we're going to call this average happiness. And I'm appending the _E just to remind myself that this is the daily diary data and it's the end of day reports that they do in the evening. So with the daily diary data, we're going to take our happiness variable, and for each participant, so for each ID, we're just going to take the mean. And again, you can look up the na.rm, the meaning of this code and what it does to missing data. But this basically just allows you to create a mean, and it will just skip over missing data. So when we run this, at the end of our data set, we now have an average happiness variable for each person. So this is the same value for the 21 days of this person. And it's, again, the same value for person 2's 21 days. And so the point I'm trying to make here is that we have kind of taken this time varying variable of happiness. And for each person, we now have one value that tells us something about that time series. In this case, it's the mean of that time series. We're going to take a closer look at this. And you'll notice that it's redundant to have all 21 rows for each person because the value is the same across all rows. And so we're going to move to a short data set where we just have one row per person. So that's what we're doing here, basically saying I don't want ID in my data set to be duplicated. Now we have a data set with 78 observations, which is the number of participants that we have. Okay, so now that we're at this short data set, we're going to describe this average happiness variable, this mean happiness variable. And in the literature, this would be called the intra-individual mean, if I haven't said that already. And so the mean, so the average, the sample's average I mean for happiness is 78.6. And remember, the scale goes from 1 to 100. So people are doing pretty well on average. The minimum value looks like it is 21.59. So there was at least one person who's kind of on the low end of the happiness scale for most of the 21 days. But let's, instead of relying on this bare bones description, let's plot a histogram where we have the intra-individual mean of happiness for everyone in the sample. And again, you get the image that You know, most people are at least above 50, but there are some people down here indicating that they have low happiness throughout the study. We're going to look at this for one individual. Let's go back to our favorite participant 105 from the previous data lab. And let's plot their happiness across the 21 days. So we're going back to the time series data. We're no longer in the short data set. But now we can draw a line at their mean value. And I just opened the data set and looked for 105 and found their mean, which was 74.71. And so the only thing we're adding to this plot from the plots we did in DataLab3 are we're adding a horizontal line, so geom H line, H for horizontal, and the y-intercept, so it's going to be going across the y-intercept at the average value, so the I mean for this person. We're going to make it a dashed line, just so it's easier to make out against the line for happiness. It's going to be fluctuating. It's going to be red. And this is also an instance where having a point is going to be useful as well. So I'm doing a geom point line as well. And this looks like that. So for this individual, oh, I think I also added a Y limit. If you didn't get a chance to look that up for the last data lab, if you want to specify the Y axis to go from, you know, the whole breadth of the scale from 1 to 100, you can just do something like YLin. So I'm saying starting at 1 and going to 100. Otherwise, it would default so that it kind of cuts the axis off to be at around 40-ish. Okay, so this is the individual's time series. And by taking the average, we get this one value to describe their time series. And it gives us a general sense of like, okay, this is how you generally feel. That can be useful in some situations. We can do it for another person, just for comparison's sake. And they have a slightly lower average, which you can see by the changing placement of the dashed line on the y-axis. Again, I manually imputed it just by looking at the data set, right? So it's capturing something that might be interesting. One thing, so yeah, so it captures a person's average level of functioning, in this case, their average happiness across the 21 days. It's a simple measure that we're all familiar with. We all kind of have an intuitive sense of what the mean is. There are some potential limitations though, or some reasons that you might be wary of the I mean. For example, a person can get a mean value that says their average mood is like 70. But it could be a value that they may never have actually endorsed throughout the entire 21-day period. And you can kind of get a sense of what I'm talking about by looking at these data. And this is part of why I put the geom points here. So here you can see that this person did endorse values that were basically at their average twice. This person did it like maybe once or twice, but you can see that there could be instances where it's really just capturing, you know, again, the average. It might not be an actual value that this person has endorsed at any point throughout the entire 21 days. And there's something weird about that to me, but it is simple, it's useful, and it is one of the kind of first ways I would describe or quantify a time series when I'm first starting to look at my data. Okay. The second most popular one, and you'll see this a lot in the literature, is to take the intra-individual standard deviation. Let's go check out that table just to give you a sense of what this is. I'm sure you've come across the standard deviation before, but now it's the standard deviation for an individual's time series. And so this is what the equation looks like. Don't be afraid of this. The point that you kind of want to focus on is the fact that it's taking the positive affect rating at each time point, so the time t, and it's looking at how this deviates from the mean positive affect. So you're basically getting the sum of all squared differences. So it's squared, so it's going to be a positive value. Between a particular affect intensity rating, so this is a particular one, it's at time t, it's the current time point, and the mean level of that affective state divided by the total number of completed measurement occasions. Okay, and like the substantive description says, it's capturing the average emotion deviation from one's mean level of positive affect. So let's see what that looks like in our data. So the code is very similar to before. Instead of having mean here, you just put in SD for standard deviation. And I'm calling it SD happy. So when we run that, again, if you're neurotic like me and need to check your data after everything you create, you can go to your data set. And again, you'll see just like the average happiness variable, each person now has a standard deviation of their happiness. And it's the same for each day of their 21-day protocol, but it does change from person to person. So this person has a very low standard deviation. This person has a higher standard deviation relative to this person. And again, we can go to a short data set since it's the same value across each day of data for each person. And we can describe this to get a sense of the kind of average intra-individual standard deviation. I have it written up there. So it's intra-individual standard deviation, sometimes shorthand as ISD. And so the mean standard deviation is 14.19. Doesn't mean a whole lot until you kind of take the min and max into account and the range of your original variable. But we can plot a histogram to kind of see how normally distributed it is and where folks are falling. Okay, so this person has the highest standard deviation of their happiness. So this could be an interesting place to look. And so rather than telling ggplot to make me a plot for participant 105 or participant 107, I'm saying make me a plot of happiness over the 21 days for anyone in the sample with an ISD of happiness that's above 32. A point of potential confusion, when I'm going to ggplot, I'm using the long data set because I'm interested in looking at the whole time series. So each row matters. But when I'm looking at descriptives of the standard deviation, I'm in the short data set. So that's why the difference is there. Okay. And so this is what the standard deviation is capturing. You can see that there's this is missing data. They didn't complete day 4. You can see that they are using the full range of the scale. They're going from a happiness of 1 on some days to a happiness of 100 on others. And so the fact that they have a high score on this ISD tells us that it's working nicely, and it's giving us information that we think it should be giving us. It would be a good idea, and this could be a way to practice, to see what the plot of a person with relatively low ISD looks like. You would expect them to be have a much smaller range of movement around their mean. Okay, so kind of taking this all together, it's telling us the average deviation from one's mean level of a variable. And in the wider literature, and we'll talk about this in the seminars, this has been conceptualized as a lability, a plasticity, an instability. So people have kind of taken this intra-individual standard deviation metric and kind of used it to try and get at theoretical notions of inconsistency in emotional responding or anything really. And so the challenge is to, and the fun part is to think about if you were to take the ISD of a time series of a variable that you care about, of a construct that you care about, would those dynamics be useful to you in your theories, either theories that already exist or ones that you make up? There is a note of caution in cap locks right here. And this is because when you plot, and so here I'm doing a scatter plot, so it's ggplot. On the x-axis, I'm going to have intra-individual mean of happiness. And on the y-axis, I'm going to have the intra-individual standard deviation of happiness. Because I'm looking at these between-person variables, I'm in the short data set, and I'm doing a g on point. This is what makes it a scatter plot. I'm also going to add a fit line, which just makes it easier to kind of think about the linear association between two variables. So that's what this kind of plot looks like. And what you can see is that there is at least you can eyeball like a linear association between the intra-individual mean of happiness and the intra-individual standard deviation of happiness, such that people who tend to be happier on average tend to have fewer fluctuations in happiness across time. And if we do a correlation for that, so core.test is one function you could do where you can plug in your x variable and your y variable, and it gives you this result that I copy and pasted here. The correlation is minus 0.4 almost, significant, etc. And so this is not necessarily a problem. The fact that there's an association between the I-mean and the ISD, there could be conceptual reasons for this. Maybe being able to kind of maintain consistent happiness makes you happy. It's easier to cope with challenges because your behavior is predictable, for example. But there are mathematical properties that lend the ISD to becoming confounded with the mean. And so I've left two references here that you can check out if you end up going down this road, just to be aware of. And whenever you look at the intra-individual standard deviation, you really want to at least control for the mean to make sure that you're not just capturing something about the mean and being led to believe that it actually has something to do with the standard deviation. That might not be the case because the ISD and the I-mean are so correlated. Or you may consider taking an alternative measure of variability or deviation around one's mean. And so a common one is the coefficient of variation, which is simply the standard deviation divided by the I-mean. And so I've just called it cov happy here. There's also a relative dispersion measure that's sometimes used too, and it's actually in the table. So you can check that out if you want. And there's a paper here that uses the coefficient of variation, so you can get some more information about that. That's just a caveat. So you always want to look at whether they're correlated and what that might mean, whether it could be something substantive or whether it's just a confound. All right, so the last index of intra-individual variability I want to look at in today's data lab is the mean successive squared difference. So we've looked at the mean and we've looked at the standard deviation so far. The mean and the ISD are time independent. And by that, I mean that if you shuffled around the scores, so if you shuffled day 21 with day 16 and day 15 with day 1, like the ordering of the fluctuations, and then you computed the mean and the standard deviation, you'd get the same answer. It's not capturing any information about time-dependent fluctuations. So how it doesn't care about how the way I change from one moment to the next. Yeah, that's probably, there's no point in going any further. I think I said everything I needed to there. But the next one we're going to look at does take time into account. So for these ones, if you were to shuffle the order of the days, you would get a different result. And so for the mean successive squared difference, again, there's a function to get at this. You just swap out SD, which we had above, with MSSD, which stands for the mean successive squared difference. And I'm calling the MSSD of happiness. Okay, so this gives you the mean of all squared differences between two successive ratings. And if we go back to the table in this great paper, you can get a sense of this. And so again, don't worry about like all the mathematical magic that's happening around here. The main thing to focus on is that you have positive affect at time t minus positive affect at t minus 1. And that just means the current time point minus the previous time point. These are measures or scores on positive affect that are side by side. So if you were to shuffle the data set, you would get a different answer because you're no longer looking at positive affect scores that are side by side. Notice also that they're squared, so it's going to be a positive number. And this, rather than the standard deviation, that just gives you a sense of the deviation in general. This captures the average change in emotional intensity between two successive measurement occasions for positive or negative affect, whatever your variable is, in my case, happiness. Okay, so we did that. Again, if you go to your short data set and you check to make sure it works because you're neurotic like me, you'll see that, yeah, you have your mean successive square difference. I'm in the short data set, so it's one row per ID, and it's just one value that captures something about the dynamics of your time series. So we can describe this for the sample. And so you have a mean value of 331. It's super dependent on the range of the scale you're using and how people are changing across time. It's still useful to look at these just in case anything crazy pops up. But again, the histogram, I think, is usually the way to go here. So you can see that most people are around here, and then you have this outlier over here. So we're going to see what's happening with this person. So I'm telling ggplot to show me the time series of happiness for people with MSSD values above 2000. And so that will isolate this person. And it's actually the same person who had the high value for standard deviation, which we'll get into in a second. But what the MSSD is capturing is the range. So just like the standard deviation, it's capturing information about the range, but it's capturing information about these abrupt changes because it's getting at time 1 positive affect minus time 2 positive affect and then squaring it. And if we look at someone who is closer to here, so let's pick up this guy and see what we get. Again, you have this kind of abrupt changes. And if you want to take someone down here in your own time, it would be interesting to see if you don't see that many abrupt changes. And that would indicate that the MSSD is doing what we hope it should be doing. Okay, so the MSSD gets at variability and instability, or like, acute changes. I find it harder to interpret than the intra-individual standard deviation, especially when missing data is present. Like if you don't have adjacent time points to get at the mean successive square difference. And I want to know exactly what the function is doing with that missing data. And that's easy to find out. We can look into the functions. But the nice thing about this is it does capture some information about instability is, I guess, a dynamic construct that it could capture to a better extent than variability that doesn't have that information about time point to time point acute changes. Okay, so we've computed 3, the intra-individual mean, the intra-individual standard deviation, and the mean successive square difference, and the coefficient of variation, but that's just a riff on the standard deviation and the mean. And actually, let me put that in here, because now what we're going to do is we're going to look at the correlations between all these things. They're not the exact same things. You can see that there are different equations associated with the construction of each metric. And looking at the plots, it seems that they're getting at different types of information. But as you saw in the example of the person with both high ISD and high IMSSD, they're not completely different from one another. So whenever you're looking at, whenever you're trying to isolate one dynamic construct, so like the MSSD as the most important thing for explaining something like depression, you want to make sure that you are controlling for everything else. So one thing you would want to do is run a correlation on all of these variables to look at the extent of overlap between the different indices. And all right, so we've computed 3 indices: the intra-individual mean of happiness, the intra-individual standard deviation, and the mean successive square difference, and actually a 4th as well, because we computed the coefficient of variation, which was just taking the standard deviation and the I-mean into account. And so one thing we will want to do is look at the correlation between these 4 different metrics. They're not the exact same things. We know that because we've looked at the equations and you've computed them. You've looked at how they kind of turn up in different plots. But it is important to see just how much extra information you're getting with each additional metric. And so a kind of good place to start is just looking at correlations. So a package I like for looking at correlations between variables is a performance analytics package. If you haven't installed it, you can do so by uncommenting that. And I'm going to subset the short daily diary data set so that I'm looking at just the 4 variables that I care about, the 4 intra-individual variability indices. And then this is the function, so it's chart.correlation. You just have to put in the IIV. You don't really need to change anything else. And it gives you a nice little kind of figure that gives you histograms, correlations in actual scatter plots, and then numbers of correlations. And so when you look at this, you can see that the mean successive squared difference is pretty overlaps quite significantly with the standard deviation. You're talking about a correlation of 0.8. That's not surprising since both capture information about variability, but there may be a little bit of extra information about instability that the mean successive squared difference is getting at because it's taking time into account. The mean successive squared difference is not as correlated with the I-mean as the standard deviation is. So that's something to think about. And then you can see how the coefficient of variation is correlated with stuff. So I would always kind of look at this just to know your data. But yeah, with those caveats in mind, you now have a couple of ways of describing the time series and quantifying between-person differences in different aspects of those time series. So for homework for next week, you want to just go through and swap out happiness for a variable that you care about, and plug in descriptors for that variable. And also plot those variables. It would also be useful in instances where I just plotted a person with like the highest MSSD in the data set. If you looked at someone at the other end as well, just so you have a good sense of what each index is capturing. And then, as you're going through the week, just think about whether any of these constructs, also thinking about what we learned in the seminars, that could make sense in the context of the things you care about in terms of the research questions you ask. And that will be a fun thing to talk about next week. All right, have a good rest of your week.